Hi, everybody.
Hello.
Oh, I am. I didn't start my video or my thing. Hey, you can see me now. Um, so we're gonna continue on with groundwater systems, and today is we have 54 of you guys here. Truthy's still taking attendance because you guys know every time you come, it's like half a point. It's in the syllabus. And I was just thinking, because I was looking at the Purdue page, Tuesday, April 13th is a reading day. Is that correct?
I believe so, yes.
You guys don't know? I'll open the chat box. I don't have the chat box there. I'm just sort of waiting until everybody gets online. It's next Tuesday, I think. Yeah. So you guys, for some reason, they scheduled a Tuesday and a Thursday as reading days, and then a Monday, which seems unfair because that means that if you have a class on a Tuesday and Thursday, that means you're missing a whole week of that class. But you're only missing one period if you have it on Monday, Wednesday, and Friday. So what I was thinking about is being generous. And since we have not had like days with tests, and we haven't had like review days for exams and things like that, because everything is just based upon homework. We have gone over homework, but we would do that in a normal class anyway. I was thinking about just canceling class on Monday to give you guys a little extra break, since you have a reading day on Tuesday anyway. It's just like a little bit of an extra break. What do you think about that?
Yes, that'd be great.
One person said it. Okay, now you're starting to write in the chat box. That sounds great. Would the homework be due Wednesday instead then? We could debate that. Would you want the homework to be due on Wednesday instead?
I would appreciate it.
You would appreciate it. Shruti, do you have all of their other homeworks graded?
Yes, homework 4 almost done.
Homework 4 is almost done. This is homework 5 or homework 6? I can't remember.
This is homework
6.
6,
Six,
yeah.
right? So you still have one more to do.
Yes.
So let's push it back. That would make sense. If we're not going to have class on Monday, we'll push back the homework due date to Wednesday also.
Yes, that's better.
Does that seem reasonable for you guys?
It does, thank you.
Okay, so we will cancel class on Monday, so don't show up. If you do, nobody will be here, or you can log on and talk to each other if you want to. I won't be here. But we won't have class. We will have class on Wednesday, and the homework will be due on the 14th. You technically are following my little schedule here for the semester. I've got the whole semester here. Today is the 9th. That means that next week, the week of the 12th, the 19th, and the 26th are the last 3 weeks of the semester, and then you have exam week. We don't have an exam in this class, so I will give you another homework assignment, but you won't have an final exam. So we will just have 3 more weeks of class, but we're going to skip the 12th. No class on the 12th, That means that we'll have 6, 7, 8, 8 more periods, and that'll be fine because I'm ahead of my. Another reason for canceling the class is I'm way ahead of where I usually am in the class. I'll give you some additional things. I may also teach you a little bit how to use Math CAD, just because some of you may like it, and it is very useful. So I'll spend probably a week on Math CAD, and we'll finish up groundwater stuff, and then we'll do some other things. Okay. It may take 2 more days to finish up all of the groundwater stuff, and then I'll give you a homework on groundwater. If you, Shruti, if you haven't queued on the homework, what does that mean?
Oh, sorry, I meant to say that I will hold office hours on Monday, and if they have any questions, they can.
Oh, okay, that's fine. So you can log in on Monday. Shruti will be here during this class period. So if you do want help with the homework, she'll be here. She'll use this class period as a homework help period. Okay. But do you want them to log into WebEx, or are you doing it through something? Have you been doing the homework through something else?
I think I'll do it through Zoom, and yeah, I'll probably just pick up the class hour to hold it over Zoom.
Okay,
I'll do
so
it for
she'll
2
do it through
hours.
Zoom. So look on Brightspace, she'll add something there.
Yes.
If you, Shruti, on Brightspace, also just say that the class is canceled, but go here to the Zoom for if you need homework help. Okay?
Yes, I'll do that.
And then just remind them that the homework will be due on Wednesday.
Yes.
Okay, sounds good. So I am going to put you guys, I'm going to share my screen now and finish the notes. But I'm going to share a few things. The first thing I'm going to share is something that I posted in the notes, because this is a nice little video. It's a GIF file, but it's a nice little video. Can everybody see the screen?
Yep.
Okay, so there's two cases here. This is a visual groundwater. This was created probably 20 years ago by somebody. But there's lots of examples. You can just Google groundwater flow systems and come up with lots of different examples on groundwater flow. So just looking at this, you should be able to tell me the differences between the right-hand side and the left-hand side as far as the aquifer goes. Some characteristics of the aquifer. Some of those words we talked about. Anybody? All of the flow lines here, well, we're pumping from this well right here. The yellow is a monitoring well. So the blue here is an extraction well. We're extracting water from it. We're filling up this box with water, with contamination. So the red is the contamination, but you have degrees of contamination. So where it's blue, it's less contaminated. Where it's red, it's highly contaminated. And you're putting it in both boxes. So this one obviously pulls it out faster than over here, but you're extracting water at the same rate from this point. So the two things that you notice is the flow lines here. These lines are lines of equal potential, which means, hey, I got a cone here of depression because I'm pumping water out right here. So that means that the water's flowing. In fact, I'll ask you guys, which way, just looking at the right-hand side of this, which way is the water flowing? In the general aquifer, which way is the water flowing?
Into
Right
the
to
center
left.
of that box.
it's flowing to the center because that's where I'm extracting, but the background gradient of the groundwater, which direction is it flowing? Can you tell? These solid lines are lines of equal potential, which means the water table is at the same elevation along this line. This line is equal potential too. This line is equal potential too. These concentric circles are equal potential, which means, like I said, I have a cone of depression right here. But this background, in this background, from this point to this point, which way is the water flowing? It's obviously not flowing along this line because the water elevation is at the same elevation along this line. But can you tell which direction it is flowing? The answer is yes. How do I know? You have to be detectives when you're doing environmental work. Look at these lines. It takes longer to pull the water from this point than from this point. And this lobe is actually lower now and out of sync. So the water from up here is getting to this well faster than the water from down here. That's because the background water is flowing from up here to down here. I'm just having a cone of depression about this location, which means this is a higher elevation, a little bit lower, a little bit lower, a little bit lower, a little bit lower, a little bit lower. And then as I go into this cone, it's a little bit lower too, because it takes longer to pull the water from here because normally this water would be going down this way. But since I'm withdrawing, I start the flow backwards here, going this way. But this water is coming this way and it's already flowing along this path. So actually from here to here, it takes less time because I've got the water flowing down this way and it pulls in water from this location faster. Out here, it's pulling it sideways because it's also flowing down. It's also still flowing downstream. So I get both the flow, the normal flow of the groundwater and the pull of the well in this direction, which is why, and I get these lobes because it's pulling it from this place, which is the largest distance. They really should, rather than do this in a square, they should do it in a circle, right? So that you can see equal distance lines. Over here, so this is one of the words that we talked about last week. This is a homogeneous aquifer because my flow lines are nice and even and everything else. And you can see these little dotted lines are actually the flow lines too, or they're telling me the direction of flow. So this is a nice homogeneous aquifer. It is. This one is obviously heterogeneous. And so it's got these places here, red and things, that are probably supposed to indicate hydraulic conductivity, places of different hydraulic conductivity. And so as a result, it's pulling water in at different rates here because the water is moving through the formation at different rates. So I got a heterogeneous aquifer over here. This is a pump and treat type system where I'm pumping the water to this well and then treating it. And this is the idealized system over here where I got a nice homogeneous aquifer. The real aquifer looks something like this because it takes a much, much longer to pump all of the water out of this area because of the heterogeneity of the aquifer. Some water comes in fast and then I'm just pulling in clean water. Some water comes in very, very slowly, and it takes me a long time to decontaminate some areas over here. So this example is supposed to show you the difference between a homogeneous aquifer, sort of an idealized aquifer, and then a real heterogeneous aquifer. And these are the monitoring wells. So you've got a monitoring well 13 and 12 here. Here's 13 and here's 12, showing you what the concentration is at this monitoring well. And obviously here it's already cleaned up, so it's down already. But over here you still have a lot of stuff going on because of the heterogeneous nature of that groundwater. I might as well show you this one other thing, which is a Excel program that I put online too, which it does, this program does one-dimensional. That program I just showed you is really three-dimensional because it's showing you X, Y, and Z coordinates, or X, Y coordinates, and then Z is with depth. So it's really maybe two-dimensional, but assuming that it's horizontally homogeneous or the same, I guess. This is a one-dimensional model. And if I go to developer here and go to this, you can find out where this program is from. It's originally from this document from the U.S. Department of Agriculture Research Service Technical Bulletin from 1982. It was originally programmed in Fortran. All I did was I took the Fortran code and I made it some Visual Basic code. It's the analytical solution to 1D solute transport with the advective dispersion equation. And so that's all it is. And you can see it doesn't take long. It's not very long. It's got an extra function here to calculate a few things, the error function and things like that. So all I did was just translate it out of this Van Genooten document. So that's the code. It's quite small. But here are some the input parameters, and I can change any of these, and then I can click the button to rerun it. And you can see it's printing it out at 4 times. So I've got an aquifer that goes from 0 to 60 meters, and I'm printing it out at 620 days. So this green, it tells me what the profile of the contaminant is in the subsurface after 620 days. And then it does quarters, 465, 310. So after the first 155 days, the profile looks like this. After 310 days, it's moved downstream, downfield in the aquifer some, because I've got a pore water velocity of 0.25 meters per day. So obviously, if I increase this to 0.3 meters per day and reran the program, it would move things downstream, downfield just a little bit, so that you can see that now my water velocity is higher, so my chemical has moved down. This is the retardation factor 7. I could make it 5 and rerun it, and basically it would run, the stuff would move downstream further, okay? Because obviously I have a lower retardation factor. I could put my retardation factor up to 10 and run it, and then I squeeze everything back up to close to 0. So my contaminant hasn't moved into my aquifer very much. Right now, I am using a 3-day duration pulse. I could change that to 7 days. Let's see if that works. And so it's a 7-day pulse. Let's do a 20-day pulse. 20-day pulse. And that means it's starting to actually flatten out at the top. I could do my end time. Maybe I can change this to 320. Yeah, so now it moves it up close, but the width of this is the 20 days because I'm putting in at 0, 0, I'm putting in contamination for a 20-day period, and then I stop it, so it goes down to 0. So if I wanted to, I could probably up this to 40 days. And then basically you can see that right now at 40 days, I still have some stuff at this point because this is an 80-day pulse. And you can see, I think I could even make this 80 days. Let's see if it runs. It may not. Nope. And it crashed on me. I have to make it lower. And it's good, it ran. But you can see what happens if you change the retardation factor. Right now it's 10. If I make it 5, much less, everything's going to move downstream. Again, this is a snapshot at time, so these curves are perfectly symmetrical upstream and downstream, because it's the midpoint is from 0 to here. My retardation factor controls that distance that it's moved. The flow rate and the retardation factor determine how far downstream it is after my, in this case, 320-day period. So if I would monitor it at 60 where it's coming out, obviously this material would come out first and then this material, but this material on this downstream side would be back diffusing, so I would end up getting a tail. So that's why we get tails out of GC and LC chromatograms, because we're monitoring it as it's coming out of the porous media, not as it exists in the porous media like this. So our retardation factor basically just, hey, all it does is adjust where the peak here relative to the flow rate of the water, okay? So you can change things here. You can also actually put in first order decay. So right now I've got the first order decay constant set way down. If I change it to that, let's see if it runs. Yep, it did. And now I get decay in my column. So now the area under these curves are not the same, because at longer time period, I have less mass of chemical because I've got a first order decay going on in the system. So you can change the decay rate, you can change the pulse duration, you can change the retardation factor, you can change the maximum printout time, everything else. So this just shows you the analytical solution for our and so now what we're solving again here is because we have first order decay. Let me see. I thought I had it here, but I don't. Notes. Let's go back to the notes. In our groundwater system, we're talking these notes right here. This is what we went over last time. It's actually not this equation. It's not, it is this equation right now that we're solving. So dCdt, because it's a function of time, the dispersion is a function of distance. This is our advective flow, our retardation factor, and we have a first order decay. So it's this equation right here that this program is solving. So I'll put this down here so you can see it, and then I'll go back to this program. So this equation is what is being solved here. And because I have a first order decay constant here, and I have a dispersion coefficient, I have a pore water velocity, so I have advective flow. Okay, so you get the idea. This equation is what I'm solving the partial differential equation rather than assuming steady state here, because I'm doing this at different times. This is my time of output. So this 320 is at a given time, I'm setting my time to be a constant value there, and then I'm solving for C as a function of X. And I can do this I'm doing this at 4 different times, okay? So you get the idea. So we solved this, but you saw that all the retardation factor does, it slows down all 3 of these processes. So our retardation factor is actually an important concept. Last time we calculated some of these values for naphthalene and toluene, and then we did it also for, I think maybe we did it for DDT. Did we? Yep, DDT here. With the concept that DDT is not a groundwater contaminant, it's a soil contaminant because it sticks to the organic carbon of soil very, very extensively, but it doesn't move. It's not mobile in the groundwater because it absorbs so strongly to organic carbon particles. So see spreadsheet example, you get the idea. And here's just some calculating some for 60 meters. Actually, I'll show you this later. I've got this in another handout. But going back to this equation then, so this is the equation that program solves with the reactions being a first order decay. And we can write this term again as a change, take this differential squared and bring out the change. And so we have this over delta x. This is another way of writing this term. So let's discretize this and look at them as being slopes, because we know dc dx is a slope. So this is a change in concentration over time. This is a change in concentration over a change in distance. And then we have a change in the slope over a distance. So over here, to do this, it's easy because we have a change in concentration with distance here. So at this point, here's x equals 0, here's x equals 1. And if we have a flow going in this direction from a low x to high x, that means this concentration is eventually going to come over here. So this whole gradient is moving sideways. This is advection. So you can see that if we're looking right here at a location, upstream we have, or down, upstream we have a larger concentration, so that larger concentration is eventually going to reach us. That's what that's saying, change in concentration with distance. With this, we have a slope here and we have a slope here. So this is a high negative slope, this is a low negative slope. So from x2 to x1 and x1 to x2, the change in the slope is a low slope minus a high slope. That means we have a positive value here, okay? So this change in the slope is actually positive, which means at this midpoint, we have an increase. So, and that makes sense because, hey, everything wants to be eventually flat. So at this point only, not at this point or this point, if you have this kind of gradient, this at the next time period, this concentration will go up because it wants to be the average of these two, essentially. Okay, so a second derivative is basically looking at how is the change in the slope affecting the concentration at this point, and in this case, it would be going up. If it was bent the other way, the point would be going down. The concentration at that point would be going down due to dispersive flux. Okay, so here, like I said, hey, this line eventually will move over and be right here. And in this case, hey, increase in dispersion, and dispersion is going to be down if it's a convex thing. So this page kind of explains what these terms mean with respect to how the concentration is changing at a point as a function of time. And then we got our reaction terms here, okay? So that's it for these notes, okay? And then in the in this, let me show you this. Why did I play that song before class? How many of you have heard that song previously?
I have.
Yeah, anybody know? Well, who wrote it and what was the most famous version of it? Maybe the most famous version, I don't know, maybe not. John Denver actually sang it. And part of the reason I played it is that it was a tribute to John Prine, who died of COVID early on last year, just when it got started. He was the writer of it. And it's interesting because some of you know, if you took 360 with me, my grandfather, who has been dead for a number of years now, he was born around the turn of the century, about 1897 or so. My grandfather was born. He was of Scottish descent. His parents came over from Scotland. He was a coal miner and worked for Peabody Coal Company for most of his life in Coal City, Illinois, believe it or not. Another tie-in is if you've ever watched the Blues Brothers, they talk about playing a gig in Coal City, Illinois. So, here I wanted to show you this. This is in Forbes magazine. Forbes tends to be, hey, it's a business type journal, tends to be somewhat conservative, but here's an article in it about pollution kills more people than anything else. And that's been known for a long time, is that in China, over 300,000 people die each year due to toxic emissions from coal-fired power plants alone. In the U.S., it's a lot less, but the air pollution in China, everybody knows it's really, really bad. And that's actually why a lot of Chinese have always worn masks, is because of getting fine particles and respiratory disease. So they're just used to wearing masks because of the air pollution being so bad. So they're trying to change their mix from coal to other things. And the reason I bring this up is, it's kind of interesting. Ever since I've been alive, coal has been the predominant way we get electricity. But if you think about it, in your lifetime, it will not be that way anymore. It's just going to change. Things have changed a lot already, to the point where electric cars are becoming more popular and more prevalent, I should say, too. So anybody know the country with the most electric cars per capita? Any guesses? Norway electric cars. Let's just Google it. Producers are still noticeable in their absence, but the number of electric cars sold has soared from 3% total sales in 2012, 54% in 2020. There are 2.5 million vehicles in Norway's roads, more than 260,000 are electric, nearly 9% of the total car stock. Norway's electric car drive belies National Alliance on Fossil Fuel. This is an article about the fact that Norway's going all electric. And the interesting thing is Norway exports fossil fuel because they have a lot of North Sea oil, which they ship out to everybody else, but they use electricity in their own backyard, in their own country, because they've got a lot of hydroelectric power in Norway. So they can use the hydroelectric power to to charge their cars and everything else. So over 40. So here, Have Norway Electric. During the autumn and last, we saw an increase of up to 40% of the market share in Norway. So Norway's going electric big time, and other European countries are doing it too, but Norway specifically. So in your lifetime, you will all be driving electric vehicles. I can guarantee it. Okay. So I wanted to show you this article about, hey, it's largely air pollution, but also water pollution and everything like that. So there's jobs for you guys because, hey, there's issues on the environment with the population going to be 9 billion people fairly soon. It's close to 8 now. It's going to be 8 within the next decade, but then it's people claim that it's going to peak out at around 9 billion people. With 9 billion people, there's still going to be a lot of environmental problems, obviously, because we just keep on making more. So I kind of wanted to give you that. Before we go on to, I thought I had a few things open here, but apparently I didn't open them before class. So I've gone over the first two, and here's Pump and Treat. Let's open this one up. Okay. Oh, this is just an example of that program. So, changing some programs, what happens? New input, change this to this, change this. You can play with the program. I don't need to show that to you, but this is just it. So what is one pore volume? This is a good calculation. Let's 4 hectare site. Let's say our aquifer is 17 meters thick and the porosity is 0.3. So if you calculate how much water there is here in 4 hectares times 10 to the 4th square meters per hectare. A hectare is a cubic. It's a metric acre, right? Times 17 meters. 10 to the 3 liters is a cubic meter times 0.3 is a porosity. So everything up to this is calculating the total volume of this site, 4 hectares times 17 meters thick. And then we multiply it by the porosity to get the water. So that's 2 times 10 to the 8th liters of contaminated water. If you have a 4 hectare site that is contaminated, 4 hectares is not very large, okay? A hectare is about a football field, right? So that's about 4 football fields, 17 meters thick. To remove 1 pore volume in 1 year, you'd have to pump 380 liters a minute. Okay, take that many liters, divide by the number of days in a year, the number of minutes in a day, and you get that many liters per minute you would have to pump to get out 1 pore volume from that site. And then that is 380 liters per minute per day. That's 0.14 million gallons a day that you would pump from this site. To give you an idea of 0.14 million gallons a day, what that is, the wastewater treatment plant in West Lafayette treats about 9 million gallons a day. So this is about, what is that? 1% of the flow that goes to the wastewater treatment plant. But that's sizable because in West Lafayette, we have large pumps and everything else. So if you're just cleaning up a 4 hectare site, you're still pumping a lot of water. And that's if you want to pump out 1 pore volume in a year. And you may actually want to pump out more than 1 pore volume in a year. So pump and treat. This was in a chapter on groundwater contamination. You can ignore that. But remember I said in the early 80s is when all of this work started on contaminated groundwaters because that's when Superfund was authorized, and that's when the government starts spending money on cleaning up groundwater sites. Between 1982 and 1992, 73% of cleanup agreements at groundwater Superfund sites designated pump and treat as a remediation method. So 73% of the groundwater sites were basically pump and treat, pumping as a remediation method. They may have had to put a barrier around the site so that the water didn't run off, put a cut-up wall or something. But a lot of it was just, let's put in some groundwater wells and let's pump the water out and let's treat the water. As most of these sites, the cleanup goals is to restore the aquifer to drinking water conditions. This is not going to happen, though, in most of these sites. But the translation is the desired risk, it's hydraulic containment. And that's exactly what I showed you with that little demo. Is that you put in a well and then you pump the water out. You treat the water either by adsorption, by advanced oxidation processes, by putting the water down the sanitary sewer and letting the wastewater treatment plant treat the water, depending upon what the contaminants are. If they're oily contaminants that can be treated biologically, you may put an oil water separator as a treatment process and then discharge the rest to the to the wastewater treatment plant, but you need a permit to do that, obviously. So you get a permit from the city to discharge. And then after the water is treated, you inject it at different locations so that now your groundwater table looks like this. So the water under here stays under here. It's not going off site because we're hydraulically containing this contaminated water. And most of these sites, it's like, okay, we have a clay barrier down here or something at some point where we know we're not getting groundwater going down. And if you do have groundwater going down into lower aquifers, that's when you have real problems. If this is a recharge zone for a large aquifer, that's a problem. And if you think about it, that's one of the issues with the Keystone Pipeline. Is I showed you a picture of it where it crosses the Ogallala Aquifer in a recharge zone of the Ogallala Aquifer. It's like that's a terrible place to put an oil pipeline because if that oil gets down there, it's going to contaminate that aquifer for a long time. And it's hard to just pump out water because when you're pumping out the water, the oil is sticking. It's sticking to the contaminants are absorbing, and if it's a NAPL, a non-aqueous phase liquid, it's sticking to the soil particles and it's not coming out. So in your one pore volume, you're not going to be able to clean out the aquifer. You have to put tens, if not hundreds of pore volumes through before you get all the contamination out because of heterogeneity of aquifers. Okay. Another type of treatment here is if you have a nested well, where here I'm pumping from down below and then I'm treating the water and then I'm re-injecting above it, and so that the water's flowing this way. So I could put a whole bunch of these nested wells in where I'm pumping from below and then discharging up above so that I get a sort of a water flow process that goes like this. Tailing happens though because as I'm pumping water, the contaminants, they have a retardation factor, but that retardation factor isn't the only thing that's slowing them up, because I've got preferential flow through these pores and everything else. I've got water flowing through some areas at a faster rate than others because of the heterogeneity of the site. So the absorption, I get non-equilibrium where my partition coefficient is really a kinetic constant. I get heterogeneous formations, so that the pore water velocity is faster in some areas and slower in the others, and where it's slow, it takes a long time to clean up those areas. You got non-aqueous phase liquids. These things dissolve because it's a non-aqueous phase, like a gasoline spill. That gasoline dissolves in the water, and then to get rid of this whole napple, you have to basically dissolve the whole thing in the water, which takes a long time. And then vadose zone contamination. We haven't talked about vadose zone. The vadose zone is the unsaturated zone above the aquifer. So if I've got soil with air in it, and it could have some water, but hey, I got air pockets in it, mostly because it's unsaturated. I can't pump water from it. That's a vadose zone. So a vadose zone is the unsaturated zone. But you can get vadose zone contamination. And then how do you get rid of that contamination? Well, maybe you have to increase the water table to dissolve those contaminants and then pump them out. So contaminated groundwater sites are very, very problematic because of the tailing of contaminants, that it doesn't come out with the water. It's retarded because of absorption, but it's also comes out much, much slower because of preferential flow paths and everything else in the subsurface. Okay. Theoretical removal, yep, everything comes out right away. Tailing, it takes a long time for it to come out. And then pore volumes to remediate a contaminant plume. This is sort of a rule of thumb. This is a retardation factor. This is a cleanup concentration, initial contaminant. So there's sort of rules of thumb here on, well, how many pore volumes do I have to put through a site to clean it up? And this equation is derived from a batch flushing model that somebody developed, 1988 US EPA guidance on remedial actions for contaminated groundwater at Superfund sites. Okay. And what else? Pore volumes pumped per year at 24 sites. These are 24 contaminated sites. Here's the pore volumes pumped per year. 14 is the maximum here. 0.12 San Jose. Extraction rate 23,000 liters per minute. Huge amount of extraction, but the aquifer is huge. 310 hectares for an area. It's a huge. This one is a huge site. Okay, and they pump out 0.01 pore volumes in 1 year. Years to pump 20 pore volumes, 20, 30, 1,000. So you're basically looking with groundwater contamination. You're pumping and treating, but you're really doing containment. By pumping the water out, you're basically containing the water under the site so that you don't, if you've got a neighborhood over here and people are using groundwater sources for their drinking water, hey, you're not contaminating their groundwater because you're maintaining the contaminated plume on the site. Okay? I think that's it. So, any questions? Do we have class on Monday?
No.
Hey, okay. Okay, so I'll see you guys next Wednesday, but Shruti will update Brightspace and tell you where you can go on Zoom on Monday if you want help with the homework. Okay? And I didn't ask you if you had any questions about the homework. I guess I should have done that today. But since you have a couple extra days to do it, she can help you on Monday with it. But definitely get it done over the weekend so that if you have any final questions, you can ask her on Monday. Okay? I'll see you guys on next Wednesday then.
Thanks,
Have a
Professor.
great weekend.
Thanks, Dr. Jeffer.
Yep, we'll see you next week.